So yeah, this week we are working on lesson 8. Already at lesson 8, can't believe it. So we're going to start talking about inferences for different types of samples, but we're going to start with one sample this week. Remember basically our 5-step hypothesis testing procedure that we have to do. So these are the same 5 steps we'll use for any hypothesis test, but basically the main difference will be like how many proportions we're talking about, or means, or if it's differences, or that kind of thing. So that's the main situation here. But yeah, so basically, so you're going to first check your assumptions and write the hypotheses. So this will basically be like, is your sample size big enough, your successes and failures, that kind of thing. And then your second one is calculating that test statistic. So usually this is going to be like our z-score or t, or what of these we have. Determine our p-value based upon our distribution, and then we're going to make a decision off of that. So we either reject or fail to reject based upon the p-value, which is step number 4. And then lastly, we're going to state that real-world conclusion as our last step. So like I said, these will be the same basic 5 steps that we're always going to have, but the main difference there is that we're just going to change dependent on what the sample is. So okay, so yeah, like I said, we're talking about one sample proportions this week. So remember, I kind of hinted at the rule of sample proportions last week. Remember, we had our central limit theorem. So that's basically the same thing, except for means. So rule of sample proportions is kind of our step 1 of like our hypothesis testing procedure for proportions, for one sample proportion. So that's our main thing here. So basically all it's asking is, you know, when can we use a sampling distribution for p, estimating, you know, using a normal distribution. So like I said, same concept as the central limit theorem. This one just has to do with proportions. So super exciting. So let's kind of go more in depth with it. So basically this is the rule of sample proportions. You basically have to meet both of these criteria in order for in order to be able to approximate your distribution with a normal distribution. So all that's saying is that we have to have n times p is greater than or equal to 10, and then n times 1 minus, n times 1 minus p is, I'm so sorry, is going to be our, it also has to be greater than or equal to 10. So remember, we kind of talked about this last week a little bit, that this is technically our number of successes, and then and so these are, they have to be greater than or equal to 10, and this is technically our failures. So all we're saying is that these both have to be at least 10 in order for us to assume that the distribution of our sample proportions is approximately normal. And then our mean is basically, it's saying that our sample mean, which is what this is, our sample mean, and we're saying that in this case, if these conditions are met, then our sample mean is equal to our is theoretically should be equal to the population proportion. So because we decided that with the conditions being met. And then our standard deviation, also known as the standard error, is going to be this equation, which you'll see very often. You'll see this kind of as your second part of your confidence interval. You have your plus or minus, and then your multiplier, or your like z star, and then when you have times your standard error, it's going to be basically times this equation there. So that's our rule of sample proportions. So yeah, let's continue. Oh, yes, next is confidence intervals for a proportion. So in this case, we're talking about, do we want to use the normal approximation method, or do we want to use the exact method? And this is just something we have to decide based upon what what our situation is or whatever. So first you want, so remember, like we just talked about, I kind of got ahead of myself. I'm sorry. So we're reiterating this again. So our n times p has to be greater than or equal to 10, and then n times 1 minus p also has to be at least 10 in order for us to go ahead and start, our hypothesis testing for this. And so once again, like I said, number of successes and number of failures has to be greater than or equal to 10. And if you're not given n and p, you want to just look at your frequency table to decide this. So that's just another thing that often comes up if you're not given. Can you explain how the mean can equal the population proportion? Yes. Yes, I can. So remember, basically what we're trying to decide with the rule of sample proportions is if we can take the sample that we have and use it and like estimate it in regards to our population normal distribution, because we assume that our population has a normal distribution. So it's saying if our sample has these two criteria met, then we're able to assume that it's representative of the population and approximately normally distributed. So as you can see here, so that's going to be our population, or this is our sample mean, and then this is our population proportion. So, and remember, the population proportion is the same thing. It's our average. It's the center of our distribution. So it's just saying that we're assuming that our sample is approximately equal to our population, given that these conditions are met. And as you can see down here too, then that means that we can use our standard error using this P, which is our population proportion there. So that's the main idea there. Does that make sense at all? And please tell me if it doesn't. Yes? Okay, cool. Yay. All right. That's a good question. It is good. You're thinking conceptually, which is A+. Okay. Okay, so then this is what we're talking about. So if you had, and okay, this is what I was just saying, if you look at your frequency table and like if you don't have n and p to calculate that, then you can look at your frequency table, or you can do use n and p to decide that on these two equations that we've been talking about. And then if these are true, then we can use the normal approximation method, like we were saying, that we can assume that it's normally approximation or normally distributed if these conditions are met. If not, we're going to have to use the exact method, which isn't a bad thing, but it's just saying we have to make sure that we're more accurate in that case. So if we were to do our our normal approximation method by hand, it's basically showing us the confidence interval of our proportion is what we're trying to decide here. So this is just our normal equation. See here we're using p hat as our sample proportion in all of these parts. And then for z star, just understand the value of this multiplier is going to increase as the confidence level increases. So that makes sense because remember, if we were to use, if we're thinking of it in terms of like a 90% confidence interval in comparison to a 95%, the z star for a 90% confidence interval is going to be less than our z star for a 95% confidence interval. It's going to be larger. So same idea there. And then it's basically just saying, and then also recognize that we're going to have a wider interval if our confidence level is increasing because we're more confident that we're going to catch that population value. So that's going to increase. So that's why the value is, since we're trying to catch that population value in there, we're going to have a wider interval because we're containing a higher percent of the data. So yeah, think back to the empirical rule, less data was contained within 68% than it was 95%, and less data was contained in 95% than 99.7, that kind of idea. And your z star, obviously, like we just talked about, is going to increase with that. If you think about, 68% was -1 and 1, so then we increased it to 95%, so our confidence interval percentage increased. We also increased our z star, which would be -2 and 2. So another way to look at it. Okay, so these are just common confidence intervals that we use, or common z-star multipliers that correspond with these confidence levels. So these are, and we've been talking often about this 95% confidence interval, and we often use our z-star multipliers too. We've been calling it just a multiplier this whole time, but since we're getting a little more specific now, it is like specifically a z-star multiplier. But same idea here. Like I said, these are just common confidence levels that are used. And so if you, instead of, trying to calculate it, this is just a table to kind of have it to refer to. So, and for 95%, people often ask, can I use 1.96? Yeah, you'll get a similar answer, but we often just round it to 2 for that. First of all, because it's a very common one that we use, and then it usually comes out to more even numbers. So, okay, so the point being, when you're trying to estimate a population proportion, you have to kind of decide, what is the necessary sample size that we have to have in order to estimate this population proportion. So what is, because you can't just kind of say, well, I think we need at least 50, that's big enough. There's a like more objective way to decide how big does our sample size have to be. So this is the equation, which looks a little scary, but it's really not horrible. We're really just, the main idea to look at here is that, we have our multiplier here. Our margin of error is the big M. So remember what our margin of error is. That's going to be the right side of our confidence interval equation. People often mess this up, so make sure you keep this in mind. So your margin of error is the entire right side of your confidence interval equation. So this is going to be your margin of error, your MO. So that's the entire right side of the equation. So remember, we have, if you were to write it how we usually do, p hat plus or minus our z star, and then times our standard error. So our margin of error is this entire right side. And then another way to write it, like I just write it in a bunch of ways to see, some people understand it differently. So our margin of error is technically equal to our z star times our standard error. So that's just some different ways to write it, but remember, margin of error is our entire right side of the equation. It's not the same as the standard error. Often people just use the standard error as that. We don't want to do that. We want to make sure that we're using the entire right side of the equation. So yeah, that's going to be your denominator in this first part of the equation, and then we're going to square that and then multiply it by our sample proportion. And remember, this was p times 1 minus p. This is technically our number, amount of failures, but that's just another part we do. And then that's going to compute your necessary sample size, which is our n. And then down here, just a note, if we don't know that value of the sample proportions, we just assume that p hat is 0.5, which is kind of, it's saying that it's like dead center, 50%. So that's just another way to look at it. Just if we don't know the sample proportion. That shouldn't happen too often, but it's just a side note if you were to get tripped up on that. Okay, so so basically we're going through the steps. So first we decided if our conditions were met. And if they were, we're using that normal approximation method. And then based upon that normal approximation method, we are going ahead and trying to figure out what sample size do we need in order to conduct this and the samples that we're taking. So you find that. And then next we are deciding how we're going to do this hypothesis test for a proportion now that we met all the different criteria. So we are going to test the hypothesis by comparing data from the sample to the hypothesized population parameter. So this kind of goes back to the idea with the mean that Alba was asking about, that we have, because we're comparing our sample to our hypothesized population parameter, which is why we did our sample mean is equal to our population proportion, population, center average, basically. So that's the main idea there, that we're trying to compare the two, basically saying, can we use our sample to approximately represent the other one? So yeah, that's the main idea there. So yeah, once again, compare proportion to in one group to a specified population proportion. So, and this should be really, technically it's our sample proportion up here. So these are just examples of research questions that we could that we can answer using a hypothesis test for a one proportion. So for babies, is it, I don't know why it says born male. Number of male babies would also be a proper way to say that, but so is population of male babies different from 0.5? So this is saying, is what we found using our samples, can we decide if, because we're able to kind of decide, that it's representing the population. So do we think it's different from 0.5? So remember, in this case, we would use not equal to, because we're just saying it's different from, not greater than or less than. Handedness, if that's even a word, or more than 80% of Americans right-handed, so we're going to use the greater than sign in our alternative hypothesis. But yeah, we're just deciding about our population in the end. Remember, our conclusion's always about our population, and because we're taking our sample and using that to make an inference about the population. So that'd be greater than 0.8 for our alternative hypothesis, and then ice cream, percentage of creamery customers. If you have been to Penn State and you haven't gone to the creamery, incorrect, you need to go. But so it's saying whatever, chocolate ice cream over vanilla, less than 80%. So you use less than in your alternative hypothesis. And these are just example research questions for a one sample proportion hypothesis test. So because these are all proportions that we're using, the 80%, 80%, and then 50% or 0.5, those are all going to be proportions there. Okay, so now to kind of sum it up, we are going to basically go through the actual steps that we we elaborated on them, but to like synthesize and kind of condense it, we'll talk about each of them then. So number one, remember, the same 5 steps apply to all hypothesis testing. The only thing that changes is what we're talking about in terms of are we looking at a proportion, how many samples of a difference, are we looking at a mean, etc. So number one, you're going to check those assumptions that are specific for one proportion. So remember, successes and failures have to be at least 10. And then you're going to write that null and alternative hypothesis. And as you remember from hypothesis testing and those units that we had, our null hypothesis is always going to have an equal sign. Alternative will never have an equal sign, always some sort of inequality here. And then, so this table just kind of nicely puts it out in terms of what's our research question, how would we write those hypotheses. So this is something definitely to, look over, understand. So, and then, the last part, type of hypothesis test tells if it's two-tailed, one-tailed. And so right-tailed and left-tailed, these are one-tailed. And then directional, obviously, in which direction it's going. So yeah, that's the main situation there. So in the second, actually this should be 3. Yeah, no, just kidding. So yeah, you want to calculate that appropriate test statistic based upon what we got there. So remember how to make that test statistic. We're gonna use this equation here that if you're doing it by hand, you're just gonna have your p hat minus your null p, and whatever we're saying that there's no change from, and then this is your standard error of your null p in the denominator here. So that's how you calculate your test statistic, which we use as z. And then you're going to determine that p-value associated with that test statistic. So after you, so whatever test statistic you had and you went through the sampling process, what are we going to decide upon, like what are we going to decide that our p-value is? So obtaining a sample that deviated from the hypothesized population as much or more than the sample we have. That's kind of the definition of the p-value associated with this test statistic for a proportion. So it's saying that obtaining the sample that we got or something even more extreme. So what's the probability of that? So we, that's kind of saying like by chance that it was, so we want it to be small. That's why we want our p-value to be small in order to reject our null hypothesis and saying that there's some sort of change. So in other words, it's just saying given that the null hypothesis is true, we always make that assumption, then the probability that a randomly selected sample of n would have a sample statistic as different or more extreme as the one obtained by the p-value. So, so yeah, and then this is just talking about one-tailed and two-tailed tests. Remember, one-tailed, if we just draw that out, one-tailed, we're just looking at, obviously, one of the tails. So, if we have greater than, we're looking, our p-value will be there. We're looking at less than, our p-value will be this shaded area. And then if we're talking about two-tailed, remember, you do have to make sure you multiply whatever you get by 2 in order to, because we're looking at both sides of them. That's the shaded area there. Alrighty. All right, so the fourth one, so we want to decide then between our null and alternative hypothesis based upon that p-value. So that's why we have to do these sequentially, because we have to decide then, when we get that p-value, what are we going to do? So remember, if our p-value is less than alpha, we often use 0.05, sometimes 0.01. Then we're going to reject that null hypothesis. And then saying it's statistically significant, we found that there's some sort of change going on. So we are in favor of the alternative hypothesis if we reject the null. And then if our p-value is greater than alpha, we're going to fail to reject that null. So it's in favor of the null, saying that we think that there's, we're assuming that there is no change at this point. We're keeping that assumption. Because remember, we always come in with the assumption that the null hypothesis is true, and that if our p-value is large, saying that there's a probability that the sample you obtained was that or even more extreme than that, we're going to fail to reject that null and keep that assumption that it's true. And then lastly, based upon the conclusion you got, you just want to state a real world conclusion. Statistics isn't, just about these numbers. We're trying to decide, what does this actually mean, like in application? So based on whatever we got in step 4, if you rejected or failed to reject, that's how we're going to state a real world conclusion based upon our original research question. So that's how, remember when we did confidence intervals, our last step was always say, like, we are 95% confident that, and then go ahead and state that conclusion. So it's the same idea here. Okay, so now we're going to talk about one sample mean. So, and in the following weeks, we'll get into like differences and paired and all that stuff. So more fun to come. Don't think you're getting away from this. So, so yeah, make sure you understand these basic, the basis of the one sample, so that when we move on to the, two sample and paired samples and differences and whatnot, that you're able to already have that grasp on the bottom one. Thank you. I appreciate saying that. I tell people that, I think I'm a little funny sometimes, but when I'm sometimes I'm not even trying to be funny, but it just happens. So I appreciate that. I'm going to make sure I save this chat for when people say, no, you're not funny. I'll be like, one of my students said I am. So I make stat fun. That's the nicest compliment I've ever gotten. I don't know how you can do that, but if I'm able to do that, then yes. Statistics. It's exciting. You'll see it in your everyday life, and then you'll be like, oh, you kind of be mad because you're like, oh, this is applicable in real life, but statistics is fun. A+. So, you may not see it now, but later on down the road, it's like, when you're a kid and you don't understand what you're saying. Thank you. It's funny and smart. Guys, stop it. I'm just a tutor trying to help my students. But yeah, you'll realize sooner or later you'll see stat in your everyday life, and it's very applicable. And now, when you read an article about something, you'll kind of understand what it's talking about. Remember publication bias, though. If you see, something being statistically significant, they're making these claims. Remember, they may not always be telling you the whole story. So keep in mind, don't be fooled. But that's a side note. But that is also true. Yeah, politics and polling definitely have a common, those are something very common that have statistics in it. But you also see it, especially in the health field. We talk a lot about statistics. And that, I do a lot of research in my field because, like I told you, I'm a speech pathology major. I'm not a statistics major at all. But we see that very often in research because we're trying to find if what we found, was statistically significant, if, the samples that we got are going to be representing the population, you know, because obviously we don't always, you know, we're taking these small samples that are supposed to be, you know, representing the entire population, but we obviously can't take, you know, data from the entire population. So trust me, you'll see it everywhere. You'll use it and you'll be like, yes, thank you, Stat 200. Like I said, you're probably not saying thank you, Stat 200 right now, but one day, promise. But I'm glad you guys are enjoying your time in Stat tutoring. But yeah, okay, so let's talk about central limit theorem. This is, remember, basically the same premise as the rule of sample proportions, but we're kind of going along and talking about it for means. So we're saying, when can we use our sampling distribution of our means to estimate, you know, estimated to using that normal distribution. So remember, the last one was saying, you know, when can we use our sample proportion to be estimated for a normal distribution? Central limit theorem, talking about when can we use that sampling mean. So, okay, so, and I just said this, I hate when I do that. I get all excited and ahead of myself, and then the next slide is all explaining it. I forget that I'm so thorough sometimes when I make these, but I apologize if I'm being repetitive. But so in this case, you know, we do have like a rule of thumb that our sample size should be at least 30. That's just kind of something that's, you know, been found over, you know, many trials, and finding that sample size, this is like a large enough sample size, then we're going to be able to assume that our distribution of our sample means is approximately normally shaped. Normally distributed, well, normally shaped too. So remember, with our rule of sample proportions, we had to have those conditions met with successes and failures being at least 10. In this case, for means, we're talking about our sample size has to be at least 30. So yeah, our distribution of sample means, if it is at least 30, that's the criteria we're trying to meet, then it's going to be approximately normally distributed. We can assume that. And then, like it says, regardless of the shape of the population, you can have a skewed population, and as long as your sampling distribution is at least 30, as long as you have a sample size of at least 30, you're able to go ahead on and use that to infer about your population. So, so yeah, you have your mean. What's the maximum sample size from binomial distributions? There's not a max. You can take as many samples as you want. I don't think there's a maximum sample size. Yeah, there's never really a max sample size. So you mean for, let me see, for binomial. So you're saying, because, the conditions that have to be met, it has to be, the probabilities have to be equal. I don't recall this. Maybe. But I don't think you'd ever have a, maybe it's used for smaller samples, but I think the point being, like, no. I think the point that might be trying to get across is that if you only have a small sample, then, that's when you'd be using that binomial distribution. Just like, remember when we talked about bootstrapping, it'd be like when we had a small sample, that's why we had to take our sample and then use replacement. So that was the main situation there. So I think that's probably what's trying to get at, that if we have that, a small sample and using a binomial distribution. So I don't think it's saying, like, you can't have a large sample, but it's used if you don't have a large enough sample. So I think that's the point they're making. So good question. Great question. Okay. Of course. Yep, you're very welcome. Okay, so now we're going to be talking about getting that confidence interval for a mean. And remember, we're using, this is why, it's important to get these bases of what that confidence interval was, and then also, what our, and our hypothesis testing steps, because, now we're getting a little more in depth with them. So now we're going to go ahead and talk about that confidence interval for a mean. So same setup, you have your point estimate, which is your sample. So in this case, our sample mean, and plus or minus our multiplier times our standard error, standard deviation, standard error. So keep in mind, Let me get color that shows up. Keep in mind that as you see, for population means, our multiplier is going to be T star. So, means, if we're talking about our multiplier, means is going to use T star, which, remember, for proportions, we used Z star. So these are things just to keep in mind, terminology and symbols. And then remember, this entire right side of the equation, this is going to be our margin of error. I hope you can read that. It's kind of faded, but so yeah, and then this is going to be our sample mean. And yeah, so that's just the different parts of a confidence interval for a population mean. So remember, we're using this sample to make an inference about our population, because that's always what we're doing in the end with our conclusion. So, and then I messed up here. This is just our common confidence interval equation. So we do have our point estimate, which is either going to be p hat or x bar, but we're talking about means right now, so it's going to be x bar plus or minus our multiplier. Remember, T star. I'm just rewriting what we have at the bottom, and then our standard error, which is this part of the equation. And to reiterate, this entire right side of the equation is going to be our margin of error. Yay! All right. Let us continue. Okay, so same idea here. We can go ahead and compute that necessary sample size that we have. Final answer would be the plus. Our final answer is going to be, it's still the plus or minus, because remember, we have to get that lower bound and the upper bound. Yeah, you want to make sure you still, because remember, it's the same idea that we've been using with confidence intervals, that we're going to have our lower bound and our upper bound. So when you do that point estimate minus your margin of error, you're going to get that the lower bound. And then, because let me just draw it out really fast. That, remember, so we're going to have, when we find this confidence interval, so, if we're using the sample mean in this case, we're going to have our x bar, and then this is, remember, this is going to be our margin of error. So remember, this is the right side of the equation. So we're going to have our margin of error, and this is where we're going to our lower bound. That looked like a lever. Lower bound, and then upper bound. So you still have to make sure we do that plus or minus. So this is going to be, I was like, I don't know what I put there. Okay, so this is going to be the minus part of our equation, and then this is going to be the plus part to get this lower and upper bound. So you do want to make sure you do both of them in there to make sure you get that lower and upper bound, which is end up going to give you your confidence interval of the lower and the upper bound. Does that make sense? Yay! All right, awesome. Good question. All right, so same idea here with computing that necessary sample size for a population mean. And remember we said, for central limit theorem has to be about 30, but, there's actually, like I said, an objective way, just like there was for proportions, to compute that necessary sample size. So all you're doing here is it's a little less complicated of an equation, just because it's only one part. You're not multiplying it by anything. These are just these two are just different ways to write it. They're equivalent to the same thing, obviously, because they're equal to each other. But all this sigma with the little squiggly dude, the little mustache on the top there, it's that's all that's saying, is that's our estimated population standard deviation. So. And then remember, our margin of error, the right side of the equation, is going to be, so our multiplier times our standard error is going to be this m, and uppercase M, so that's the denominator. And then, like I said, a different way to write it is just to take the fraction and then square it. So main idea there. Okay, so now we'll once again go through those steps of hypothesis testing, but we'll specifically do it for a one sample mean. So remember, first step is we're going to make sure we check those assumptions. And we haven't really reiterated this so far, but remember, we have to make sure that data is quantitative. That means it's going to be a mean. And then, this is kind of going back to, what we were talking about at the beginning, that when we have quantitative data, we're going to be talking about means. When we have categorical, we're going to have categorical data is going to be proportions. So And then we have to have that randomly sampled, or the data has to be randomly sampled, and then from a population that's approximately normally distributed, which is where, you know, we want to make sure that our sample size was large enough to assume that's approximately normally distributed. And then and we also, by the way, we call this a one sample means t-test. If you ever see that written out, that's what we're doing here in this hypothesis testing procedure. And then once again, here's another graph or table of kind of how we break down different, you know, the different types of hypothesis testing that we're doing. So, you know, our two-tailed, again, this is the same thing as the one we saw with proportions. You know, we have our two-tailed, and then our right-tailed and left-tailed, which are one-tailed, and then, you know, our alternative hypotheses. Remember, always have an inequality, never an equal sign. And then our null hypothesis is always going to be an equal sign, because we're always saying, you know, that there's no change. So we're saying that our null is equal to, that the mean is equal to the null, you know, so saying that there's no change going on there. And we always assume that that is true, remember. Okay, so then remember, our second step is we're going to make sure that we are calculating our test statistics. So remember, for means we are using t, proportions we use z star. So all you do by hand here is use, to find that test statistic, you use your sample mean minus your null mean, and then divide it by your standard error. That's your denominator there. So, and then once again, you know, you have your key down here for what all these symbols mean. So that's just a way you can calculate your test statistic. So yeah, remember, like I said, this is a very similar equation to the equation for finding the test statistic for a proportion, but the main difference is that our sample statistic and hypothesized population parameter is divided by the standard error in this case. So we want to just make sure, you know, check that the difference there to make more sense of it. So, all right, and then our third step is going to be determining that p-value associated with that test statistic there. So you use that t-distribution that, you know, with the test statistic that you got in step 2, you use the distribution that came along with that to find that p-value. And then our degrees of freedom, which is something kind of new that we're talking about, is going to be our sample size minus 1. So that's for one sample mean. There is a different type of degrees of freedom for another type of test. Keep that in mind. But if we're talking about a one sample t-test mean, we are going to have our degrees of freedom as our sample size minus 1. And so yeah, and then our fourth step, we're going to decide the same, you know, our fourth and fifth step are the same basically for every single hypothesis test we do, no matter if it's a one sample, two sample, whatever. You know, we're going to decide between that null and alternative hypothesis dependent on the p-value we got in step 3. P-value less than alpha, reject that null. And then if it's greater than alpha, we're going to fail to reject the null in favor of the null, saying that we still think there's no change. And then lastly, make sure you go ahead and give that real world conclusion, because that's what we care about, you know, the real world. So yeah, yay. Thanks for sticking in, guys. I know it's kind of a long chapter, but you guys are doing great, asking great questions. So, okay, so paired means, like I said, we're going to start getting into, you know, not just one sample. Now we're talking about means that are paired together, so dependent on each other. So the main difference here, like I have over here, you know, note the change of the subscript of D. We are changing it from one mean. It's showing, you know, that's the main difference of all of this. You know, all the equations look basically exactly the same for our confidence intervals and hypothesis testing and whatnot for one mean, but the main difference is we are going to add the subscript of D to show that there's to show the difference between these two paired means. So as you see here, our standard deviation subscript D. And yeah, remember our t star multiplier. So we use t star for means, z star for proportions. So t star is going to be our multiplier with our degrees of freedom once again. Same as one sample mean is going to be our sample size minus 1, so n minus 1. So yeah, that's how we find our confidence interval. And remember, you know, we are going to do plus or minus, so we get that lower and upper bound in that case. So okay, so our first step, remember, for hypothesis testing in general, we got to check those assumptions. So when we're talking about paired means, we're going to go ahead and check these assumptions that we do have to have this data to be paired in order to use this, obviously. And then the difference has to be, saying it's normally distributed if it's paired, and then in the population, and then our sample size has to be at least 30, like we've been talking about. In order for us to assume that the sample size is normally distributed, we can use that to decide that. And then we do have a research question down here. We have a research questions, and then the different hypotheses and types of tests that we use. Like I said, same situation we'd be using for all the hypothesis testing, just with different symbols, and because you're using different different means or proportions or whatnot. So yeah, we have obviously this is exactly the same as our one sample mean, but we do have the subscript of D down here in order to decide that. So we can deviate that for saying that it is a difference of paired means here. So step 2, as always, we're going to go ahead and calculate that appropriate test statistic. It's still going to be T because we're still talking about means, but the main situation here, so remember, like I said, if they're paired, they are dependent upon each other because they are together, and what happens to one does affect the other. And like I said, it's the same exact equation as one sample means, except we are talking about, a difference in sample means for, this part of the equation, and then our standard deviation of the difference in sample means. So that's the main difference there. And after you check that that statistic, our T, we're going to go ahead and last 3 steps, remember, determine our p-value. Remember, we're using our degrees of freedom for as n equals 1. And like I said, 4 and 5, I won't harp on it anymore. I think you guys get it. Decide based upon your p-value and the size of it, what you're going to say about the hypothesis, and then go ahead and state that conclusion. So. Oh, okay. Ooh, I almost said research questions. Reviews. So let's try these out. So yeah, okay, let's try these. So which statement is correct about a p-value? So I won't read these to you guys. You can read. So go ahead and read through these options, and then let me know what you think the answer is, and we'll go over it. Yay. Okay, great job, guys. Absolutely. So our answer is going to be A here. Because remember, if we do have a small p-value, that's going to provide us with stronger evidence that our results did not occur by random chance. That it means that there's actually some sort of change in the population, which is why we're in favor of the alternative hypothesis. We're going to reject that null, say, no. That null be thinking that there's no change, but we think there is. So that's why A is our correct answer, because it's saying the smaller the p-value, we do have stronger evidence in favor of the alternative hypothesis, which remember is saying that there's some sort of change going on in the population. The rest of these just don't make sense. Like I said, B is saying the opposite, that's in favor of the null. Nah. And then the last two are saying, doesn't really matter what it is. And it's depending on if it's one-sided or two-sided. That's not true. Doesn't really matter in that case, dependent, to make a assumption about the null and alternative hypothesis. So our answer is A. Great job. Genius. All right, let's try this one. So based on a 2000 census, 31.8% of grandchildren in California are the primary caregivers for their grandparents. Suppose that our sample size of 200 people are able to be sampled from this population, and the sample proportion of grandparents as primary caregivers, which is our p-hat, remember, it's a sample proportion, is to be calculated. So what's our standard error of sample proportion? So hint, go ahead and apply that rule of sample proportions that we've been talking about to meet those assumptions, and then we will go over this. So try this one out. Raise the roof. Great job, everyone. This is A is correct. I didn't mean to make the last one, all of them A, but A is our correct answer because remember our standard error in we're talking about for sample proportions, it's going to be our square root of p times 1 minus p, or p hat, and then divided by our sample size of n. So in this case, we are going to have square root of 0.318. So our sample, that's our sample proportion, times 1 minus 0.318, and then divide that by n, which is 200. And then that's how we get equals, boop, 0.0329. Yay! Great job, guys. Killing it. Okay. Let's do another one. Okay, given that the average height of an NBA player is 201 centimeters with a standard deviation of 8 centimeters, if we were to take a random sample of 30 NBA players, what is the mean of the distribution of sample mean? Excuse me. What do you guys think this is? Go ahead and try this one out. Okay, don't overthink this one. So remember what we talked about with our essential limit theorem, that if we have a large enough sample size, we're able to assume that our sample mean is approximately equal to our population mean. So like this says, what is the mean of the distribution of sample means? We can assume that it's 201 because we're able to estimate that mean. That is just the population mean because we have a large enough sample size, so we're able to estimate that. Does that make sense? Their answer would be 201 in this case. Yay. Okay, awesome. Boop, boop. All right, cool. Alrighty, so we got a research question here. So what is the average weight of a Granny Smith apple? Things you got to find out in your free time. So what procedure should we use to address this research question? So keep in mind what kind of variable it is and what we're trying to find out. So you got a 50-50 shot for this one. So guess if you don't know, but try this one out. Yay. Okay, great job, guys. Absolutely. So our answer is going to be B, because first of all, our confidence interval is being used because we're estimating a population parameter. So that's, if we are estimating a population parameter, that's when we're going to be using a confidence interval in general in comparison to a hypothesis test. So, I mean, I should have kind of put some options in here about, you know, if it would be a hypothesis test for me. But remember, hypothesis tests were when we would compare the two between confidence intervals and hypothesis testing. Hypothesis tests are coming up with a single conclusion there. In comparison to a confidence interval, we're going to go ahead and estimate that population parameter with the range, you know, and being confident with it if that population parameter is within that range. And then since the weight is a quantitative variable, that's why we're going to be talking about a mean and not a population proportion. So good job. Okay, I think this is our last one. How sad. Okay, so you want to construct a 95% confidence interval for the mean risk diameter of Penn State World Campus students. Another interesting thing to find out. So, previous study examined the risk diameters of adults found in a sample mean of 10.543 centimeters with a standard deviation of 0.944 centimeters. So, what sample size should you obtain to construct a confidence interval with a margin of error of 0.1 centimeters? So, try solving this one, and then we'll go over it. Awesome. Awesome job, Hannah. So definitely this is our equation to find our sample size here. Remember, we're going to use n equals and then our multiplier. So in this case, you could use 1.960 or 2. And then we're going to multiply that by our standard deviation, our approximate standard deviation, which is going to be 0.944. And then divide that by 0.01. So this is going to be our 10%. So, 0.1, excuse me. So 0.1, because that's our margin of error. And then if you solve this out, you're gonna get like a decimal, but you remember, being realistic, you can't have a decimal of people. They're gonna be a discrete quantitative variable. So you're gonna get about 343 people. Boop. Good job. All right. The end. You guys stuck it out. Thanks for sticking around. That was definitely a significant chapter. So great job. Once again, obviously, you can go ahead and rewatch these super fun group review sessions. Skip the Netflix, watch some group reviews. Our next one will be on Sunday. Yep, Sunday at 10 o'clock and Eastern time. I know some people aren't on Eastern time, but that's us. So if you haven't given me your Penn State email, please go ahead and give that to me just for attendance purposes. We will not email you. If you have any other questions, go ahead and type them in the chat box for me to answer. And if not, have a good weekend, y'all. It's a Michigan game this weekend, so be sure to tune in. ESPN is here for College Game Day. It's going to be pretty serious, so look for me on the TV. I'll be like, hello. So, yes, have a great night, guys.